Welcome to module 36 of object oriented analysis and design. We have been talking about different UML diagrams. In the current module and continuing in the next two, we will talk specifically about state machine diagrams. So, the objective in all these three modules would be to understand the state machine diagrams, and accordingly this is the outline that we will follow. And as we have been following, the blue part on this outline is actually what we will do in this current module. Remaining parts will be done in the subsequent modules. So, to start with, we will make a quick recap in terms of some of the basic concepts which will be referred more frequently here in this module. First, naturally, the concept of the state of an object. So, we have talked in terms of an object being defined in terms of its state, its operations and its identity. Particularly, if we talk about state, then depending on the different properties that it has, then the different combination of values that the properties can take define the state of the object, and we have seen that that could be static or it could be dynamic. We have also seen that based on this there is a behavior of the object which is based on the combination of operations, which certainly are defined based on the state of the object. We continue to refer to the client server model. I am sure by now you have understood and you are following the client server model pretty closely. In terms of the SDLC phases, the software development life cycle phases, the state machine diagram is first constructed in the analysis phase. It is also called the state chart diagram. Actually, the earlier name was state chart diagram. In the recent versions of UML, this is more frequently called as a state machine diagram. So, in the analysis phase, as we analyze different sequence and collaboration information and we talk about the activity, we also extract the state based information in the state machine diagram. And as is true for most of the other models, we refine on this state machine diagram, which is a behavioral model, and get a more accurate state machine diagram for the problem at stake. So, this is the basic background, and based on this we would like to talk about the state machine diagrams. The state machine diagram is a behavioral diagram. It shows the discrete behavior of part of the design system through finite state transitions. So, quite a lot is being said here. One is, let us look at these in parts. One is, this is a behavior diagram, we understand that it defines some kind of a behavior, and it shows a discrete behavior. Discrete behavior in the sense that a behavior could be continuous as well, but here we will have discrete behavior, that is, it is defined in some terms of certain set of discrete values, and therefore, the combination of discrete values define a finite combination which we can think as a finite set of states and their transitions. And there are primarily two kinds of state machines that the state machine diagram would be involved with. One that is called the behavioral state machine, and the other is a protocol state machine. Naturally, a state machine will consist primarily of states and transitions. So, in that sense they are pretty much like, though they are substantially endowed further, but they are pretty much like the finite state machines or the regular automata that you have studied in other courses, but here they will take much more complex shape. So, first let us talk about the behavioral state machine in this module. This is a specialization of the behavior and is used to specify the discrete behavior of a part of the design system through finite state transitions. So, just think about what we are saying. There will be states, say these are states, and there are transitions between these states, and every state is has a certain behavior. So, unlike say the traditional FSM, if you think about you would have done traditional FSMs like this with 0 1 input, you have state A, state B, you say on 0 go to this state, on 1 come to this state, on 0 go to this state, and so on. You must have seen such the kind of state machines like this, and some states are defined as a final state, some as an initial state. Herein, so states in the traditional FSM sense are basically placeholder markers, which remember the kind of discrete combination of information that the particular state represents. But here we will see that in case of a behavioral state diagram, the states are more empowered. They have a behavioral feature or specification, in that a state may have certain conditions or event for entry. Every state may have some entry. Every state may have certain conditions or actions on exit, and typically they will have a behavior that happens in this state. So, this is not a state at a very micro level of the system description, that could be at a much higher level of abstraction, where a whole lot of things might happen within a behavioral state based on a certain entry and certain exit, and that behavior is what will be captured in the action for the state. So, the states in this context will often be owned by behavioral class, which is called the context of the state, and which defines the signal and call triggers that will make an entry into the behavioral state of a behavioral state machine. So, let us slowly start taking a look into some of the possibilities. So, we start with a simple one where this is a state machine of a bank ATM possibly. So, this is where you start, and when you start, the machine is in an idle state. Now, this idle state is a behavioral state in the sense that while it is idle, it is not a passive state it is in. It is still active to receive inputs, appropriate inputs. It will keep on checking if somebody is pressing some button, if somebody is inserting a card or anything like that. So, at a macroscopic level, this is an idle state, but internally it may be doing quite a few things. But then if you have a specific event like in card, which means a card is entered, then it gets into another state, which is the active state, where this is a state where it is supposed to do a whole lot of things. Basically, having been active, it will actually interact with the user and possibly allow the user to withdraw money or check balance or things like that. And when all that is done, then it will come back to the idle state, or it could be that in the halfway either the card is not accepted or the pin was wrong, or the user decides to abort the transaction that the user was doing, then it could be cancelled and it will again come back to the idle state. An alternate path could be that the machine is in idle state and it needs to be serviced, it needs to be maintained, certain preventive maintenance should be done. So, it is put into the service mode, and when it is put into the service mode, it gets into a state which is out of service state, and only when the maintenance or servicing is over, then it will again have a transition fixed, which will bring it back to the idle state. So, we could, in terms of very simple 3 states, we can at an abstract high level, we can describe a ATM application, an ATM process, and this is what is the purpose of a behavioral state machine. There could certainly be lot more details than this. We will get to more details, but let us walk through a couple of other examples. So, this is another example of a temperature controller, which again starts which again starts in the idle state, and and again what I am trying to repeatedly point out is this is not like just a finite state machine, where if it is in an idle state it will basically continue to be in the state unless some specific input comes in here. In the idle state itself, it is doing a lot of actions. It is possibly trying to, since it is a temperature controller, it is regularly collecting the current temperature value through the temperature sensors, and based on the value of the temperature, if it is too cold, it changes state and puts on the heater. So, when it state is heating, again a lot of things are happening in this heating state. The heater is on, and again the temperature is being monitored, and so when it is become adequately hot or less cold, then it says okay, heating is done, and it comes back to the idle state. It has achieved the temperature that has to be managed. Similarly, it can happen on the other side, that if the temperature goes higher than what is specified, then it will get into this cooling state, put the cooler on and so on, and on completion, on achieving the target temperature, it will come back to the idle state again. Or it is possible that from the either the heating state or the cooling state, there might be some error. The heater might malfunction, the cooler might malfunction, and it might go into the error state, and it will come back to the idle again when the error is removed. So, each one of these again at a high level describes the overall behavior of the system. So, when we capture the system requirements and start analyzing, we try to see try to find out situations where we can identify discrete states, behavior states of the system, which can in a crisp way describe the overall discrete behavior of the system that we are trying to describe. So, the behavioral state machine in structural terms consists of vertices and behavioral transition. A vertex is a named element, and which is an abstraction node in the state machine graph. We will see there are other kinds of states as well, and there are primarily two subclasses of vertices. One is the behavioral state vertex and the pseudo state vertex. So, state is a vertex that models a situation during which usually some invariant conditions hold. So, if you just refer back to let me just take you back to the let me just take you back to here. So, this is a state because here certain invariant condition hold. The invariant condition is temperature is within the desired limits. This is where some other invariant conditions hold is temperature continues to be remain lower than where it should be, and the heater is actually operating and so on. So, that is how the state will be a vertex, and so what you saw there are the different vertices of a behavioral state machine diagram. So, the behavioral states, the first of the two kinds of vertices that you have, the behavioral states has invariants, as we say, they represent a static situation. Such an object is waiting for some external event to occur, or certain a particular condition is being maintained, and it model dynamic conditions such that the process of performing some behavior, like it is in terms of the temperature controller, it is the process of heating which is regularly performing the heating operation to try to achieve the target temperature. The behavioral state in turn will be of again three kinds. They are called simple states, composite states, and sub machine state. Let us look into the definition, and then we will explain what they mean. A simple state is one that does not have substate. So, we will need to look at what are substates. We will come to that when we go to the composite state. So, a simple state is just a state. So, it has a name, that is a minimum, so which describe what that simple state is doing. But in addition, so the name is expected, but it may be optional, it may not be there. But what are the two other things is what is the internal activities that might happen in this state. That is the behavior as to where an object is in this state, what does it do. So, if the object is in a state whose name is heating, then the do action could be run heater. So, which is activity that happens during while the system is in that state. So, that is the do part or the activity part of a simple behavioral state. Besides, we will have an entry, may optionally may have entry and exit activities. For example, you are waiting for input, user input is one simple state and your entry is welcome. So, the activity when you enter this state is you put on a welcome message, and the activity when you exit the state is you put on a thanks message and so on. So, what is important to understand, and that is true for the simple behavioral state, and it actually in turn is true for any behavioral state, is unlike the state of an FSM which just remembers your internal condition as to where you are. In addition to that, it has an entry activity, it has an exit activity, and it has a performance activity, internal performance, internal transitions that may happen. So, this is the behavioral state will always carry with it certain behavior which is defined in terms of these internal activities and the internal transitions that may happen in terms of within that state itself. Now, so this is just another example. So, here you have multiple states, these are the four states, these are simple states and these are the different transitions. So, if you have water vapor, if you condense it will become liquid water, if you freeze it will become ice, if you sublimate it becomes water vapor directly and so on. You can just follow, and from your simple knowledge of physics you can understand that this kind of system can also be described in terms of a state machine diagram. Let us look into something which is a little bit more closer to the definition of behavioral state machine. This is basically for dialing a phone. So, you can see these are the different states that the phone could be in. So, in every state if you notice there is a name of the state, these are the name of the state. So, there is a state dial tone, there is a state invalid, there is a state busy, there is a state dialing and so on. So, these are the states that a phone is expected to be in. So, if it is in a particular state, then it has a do or the action activity of that state. So, if the phone is in dial tone state, then your the activity is it will play the dial tone. So, that is what we expect, right. If we pick up the phone and that is in the dial tone state and it will do that, and in which you can in this state you can dial the digits, and once you start dialing the digit you get into a different state which is a dialing state, where you could dial further digits and keep on remaining in that state. It could be that you dial a wrong digit or you dial a number which is not valid, then it will take you to a different state which is the invalid state, where the action is to play the message saying that you have dialed a wrong number or something. Otherwise, if you have dialed a valid number, then your next transition happens to connect, and that takes you to a connecting state for the phone, where the number is being connected. And there are two possibilities. From this connecting stage you might get connected, where you go to the ringing state, where your action is to play the ringing tone, or it could be the number could be busy, then your action is to then you get into a transition into the busy state and your action is to play the busy tone. Again, in the ringing state if you are in, then if the callee answers, then you get into the talking state, and then you continue in that talking state till the callee hangs up or you get pained or the callee answers. And this is how this whole state machine will define the different distinct. You can understand that if you think of the phone in terms of a digital system, then there will be several other states involved which will define how to play the dial tone, how to actually do the dialing. Every key press could involve tens of different states and so on. but we are always interested to model the system at an appropriate level, and at this level if we are trying to model the dialing of a phone or making a call, then we are most interested to identify only those distinct states that the system will take, and the actions that will happen, and what are the transitions that will take between these states, so that you get a finite behavior on this. Besides that, you have you may have an idle state when you are not even trying to dial. So, in a state from where you actually enter the dial tone state when you lift up the receiver, and a state where you basically get back into when you hang up. So, this is a simple diagram showing how you can use the simple behavioral states to define a more complete state machine diagram, state machine behavior of a system. Now, often we will find that if we just want to describe everything in terms of simple state machine, then we might find that the whole thing turns out to be quite complex or quite elaborate, and we might just want to combine couple of different states and their transitions together into a bigger state, which is called the composite state. And when you are in a composite state, then all the internal states that comprise the composite state or that build up the composite state is known as the substates or the nested states. So, here we are showing that this is a composite state, which again has a number, has a name, the serving customer, and serving customer has a customer authentication state and a transaction state, and within that again a lot of things could be happening. But this as a whole is now a state where you say that this is where I enter and this is where I finally exit, and I have substates of customer authentication and customer and doing the transaction, and this can happen, this substates can happen in a sequential manner, disjointed manner, like it is happening here, or it could happen in a concurrent or orthogonal manners. It could happen in terms of what is known as different regions. A region is in a composite state is a collection of states and transitions that define one state machine in that part, which is giving you that composite state. And in terms of these composites and composites of composites and so on, we can very compactly represent the state machine diagrams. Now, composite states could be orthogonal. They are called orthogonal if there are more than one regions, that is more than one independent threads of execution that happen in the composite state. And when we have that, we can actually show the substates in terms of just a symbol instead of showing the details. In the earlier slide, we showed the details of serving customer. Here we just show it as an icon, meaning that there are substates in this which describe the details of the serving customer. So, this is kind of the composite state you might have. This is a non-orthogonal composite state, which means that this has only one region. So, this is only one thread of execution, this is where you start, and these are your substates. On certain event 1, you change from substate 1 to substate 2, on event 2 you change back, and on event 3 you terminate. Whereas, in another kind of composite state which is called orthogonal, you will have more than one region. So, this is one region and this is another region. These are the two different regions, and they are typically shown by separate dotted lines. And you have substates in region 1, you have substates in region 2, and you have events transitions happening between them, but these are independent. So, these are kind of this what is happening here is in concurrence with what is happening here. So, in time domain they are happening as concurrent events, and when that happens, then we say that is a orthogonal composite state. So, this is one example of a human life. So, these are two orthogonal two regions, one region of personal life and one is region of professional life, where you can have multiple different state transitions happening between the substates of the composite state of human life, single, married, divorced, whereas on the other one unemployed, employed. So, these every region will have certain different thread of which will act independently on the overall composite object. So, you could show this in terms of disjointed substates as in here, or you could show them as parallel substates depending on if they are shown like this, they are disjointed. If they are shown as parallel, so they are like different regions and they happen concurrently. So, these are the different notations that could be there. Finally, a third kind of so in terms of the behavioral state, we have seen simple state, we have seen composite state, we have seen simple composite state which has only one region, or non orthogonal composite state, and we have seen orthogonal composite state. The another that is commonly used in the representation are called submachine states. So, you can define submachines of a machine and actually define properties based on that submachine. So, let us try to look at an example that will be easier to understand. Say we look at the ATM itself. So, the states are you verify card, and once that is accepted, the card is verified, then you read the amount and do the transaction. And the outcome could be that the transaction is aborted, where you move to card released, the something goes wrong. So, you go to out of service, or you actually succeed. So, the transaction is verified and then the card is released for card release. So, this reading amount and actually doing the all those balance check and all that is shown as one state, but is actually another state machine itself. So, that we mark this as read amount SM. I am just writing SM to indicate that SM is a sub machine. So, read amount SM, you will expect that there will be another state machine diagram which gives the details, which says how to select the. So, when you are accepted the card, then you are here and you have select the amount, then you check if the amount is okay, you enter amount and all that, and at the end you could either remain reach the final state, which is success state, which is here, or you could reach the abort state, which is here. So, submachines are very frequently used, so that so if they are like the submachines are like function calls, they are like subroutine calls. So, you are saying that here I have a submachine, and this same submachine could be used in multiple other state machine diagrams as well, behavioral state machine diagrams as well, and they all will by the name refer to the same submachine where we have. So, submachine state are states which basically have a complete submachine diagram incorporated in terms of them. So, given this is a behavioral state diagram of an ATM. I will not go through the details, we have just briefly discussed this, and I would request that you please go through each of these state transitions and get comfortable in terms of describing a ATM system through this kind of an FSM. So, to summarize, state machine diagrams have been introduced. We have talked about what are state machine diagrams are, and we have given an overview in terms of the behavioral state machine diagrams, particularly talking about the vertex and the different behavioral states, the simple state, the composite state, and the submachine state. In the next module, we will continue discussing about other kinds of states in a state machine diagram.